Hi, everyone. Thank you for coming to this session. My name is Abdel. I'm a developer advocate at Google. I work on Kubernetes, both open source and on GKE as a product. And today, the goal of this session is basically to walk you through some of the features that we have actually on GKE that are specifically designed for helping you run large language models in production. So I have kind of four points I'm going to talk about today. Some of the basics of running large language models in Kubernetes in general. What does this actually mean? And why is it even a topic? Some of the challenges, because if there was no challenges, we're not going to be here anyway. How does GKE help solve those particular challenges? And then a couple of conclusions. Before I get started, I'd like to know a little bit about you. So by raise of hand, how many of you run models, have run models before in Ollama on their laptops? OK, most of you. So how many of you run them in production, in Kubernetes, Vertex AI? OK, a few people. Cool. So, I mean, large language models are evolving very quickly. And they're evolving both in terms of sophistication and complexity and the number of tasks they can achieve, but also in terms of size. And the thing with Kubernetes and containers, generally speaking, is over the last like 10 years, let's say, that Kubernetes existed as a tool, the industry have been moving toward like making containers and applications smaller and smaller, because smaller container means it's faster to start, it's quicker to patch, et cetera, et cetera. And then large language models showed up and then just blew out of the water all these optimizations we've been doing, because large language models are extremely big in size. And so we're going to cover some of the open source ones, specifically open LLMs, things like Gemma 4, which I should have updated this one, or DeepSeek, or Qwen, or Kimi, or Llama 3. These are all super large, super sophisticated models. So if we just take an example of like DeepSeek, the most complex R1 model, which is the 760-something billion parameters, is roughly 1.7 or 1.3 terabytes in size, just the model itself. So before I move forward, I know that you're going to listen to a lot of AI during this entire conference. So I wanted to spend a little bit of time giving you some foundations so you can kind of more understand when people talk about this concept. So everybody knows what a large language model is, right? Inference is a term that the very simplistic way of thinking about inference is basically serving. It's the part where you take the model and then you put it in production and you start talking to it. But inference within large language models is actually an extremely complex system, because models inside of the model, there is a pipeline that takes your input tokens, decode them, load them into the cache, and then process them, right? So inference is an extremely complex system that most of the time you don't really see, because for you just run something like Ollama, run a model, and then you talk to it through a REST API, right? But it's extremely complex. And it's very important to understand what inference is, because down the line, I'm going to talk about a couple of projects that are specifically talking about optimizing the inference part of running large language models. Then you have serving, so serving or server engines. The simplistic way of explaining it is usually when you have a web application, you need a web server to run it. So serving engines are actually the web servers of large language models. They are the piece of software that gives you a standard REST interface that you can talk to, and then on the other hand, knows how to talk to the model and then get the tokens input in and then outputs back. Accelerators, I think we all know what the GPUs and TPUs. Quantization, that's a very interesting topic. Quantization is essentially a value that allows you to change the precision of the model. Most models support multiple types of quantizations. There is multiple algorithms for quantizations. But essentially, you can think about it as quantization is for you the way to change the model memory footprint, which also has a direct impact on the precision of the model. So the higher the quantization, the bigger the model is going to be, the more memory it's going to need, but the more precise it's going to be. The lower the quantization of the model, the lower precision might be. So this is something that is interesting to consider when you're optimizing large language models, that you have to think about, like, do I actually need to run my model as like FP16, which is like probably one of the highest quantizations. Weights are the numerical values that define the strengths of the neural network. So when you run large language models, you have to download weights from somewhere, usually to be able to run the model. Context window is very important. So context window is essentially the size of how much the model can process at one go. So that's usually explained or expressed in a number of thousands of tokens. So large language models, usually they hover around 128 to 256,000 tokens as a context window. If you're talking about like cloud-hosted models like Gemini, it can be up to like 1 million tokens as, in one go. And why context window is important? It's important for two reasons. One, the higher the context window, the more the model can process. So think about like a model that can do coding. The bigger is the context window, the more data you can shove to the model to be able to like, fix a bug or suggest a code change. But it also is important for people running large language models in production because the context window is basically the size of the request as your input on your load balancer, and that's important to know. And then multimodality is essentially the concept by which the model understands more than just text. Most of the models that exist today on the market, even the open source ones, they can actually understand audio, video, and images. And this is also important because we're going to see down the line in the presentation, when we are actually running large language models in production, we're not just running web apps that take as an input a JSON and return a JSON. They actually sometimes, the JSON could be a picture or could be a video. So it's important to keep that in mind when you are designing your architecture for running the models. And then most of the time, you're going to be in one of these situations. You're either going to run your model on a single host, single accelerator, so one GPU, single host, that's like the easiest. Sometimes the model cannot fit on a single accelerator, so you have to shard it across multiple accelerators. So that's single host multi-accelerators. So, and then in some situations, you are going to actually run into a physical limitation on how many GPUs you can have on a single node, because there is a limitation of how many PCI Express ports a single server can host. So you might actually need to shard the model across multiple hosts. Back to the example of DeepSeek, the biggest model DeepSeek needs, it needs roughly 1 terabyte of NVRAM. There is no GPU today that have 1 terabyte of NVRAM. So you have to shard it across multiple hosts. And so for running large language models, you're basically going to be in one of these three situations. On the far left, your left, my right, you have the easiest one, which is running it on virtual machines. So spin up a GKE VM, put the model there, and then call it a day. On the far left is or the far right for you, it's the most automated way, which is Vertex AI. You can just like literally just put in a Vertex AI model into Vertex AI, and then we give you an endpoint, and then you call it a day. GKE sits somewhere in the middle, and it gives you kind of the most flexibility in both controlling what the model does, defining your like security parameters, defining your governance parameters, et cetera, et cetera. So one of the key differences between these three things is basically GKE and Vertex AI. You can technically do scale to 0, but it's quite complicated to do. But with GKE, you can actually leverage all the Kubernetes auto-scaling mechanisms to be able to scale up and scale down very fast to respond to demand, right? So then the question is, why would you want to run your local models? Why would we just not use a cloud-hosted model on like Gemini? Well, there are multiple reasons. Regulations is the biggest one. Like you might not just, like your industry doesn't allow you to run cloud-hosted large language models. So then you have to run it in your own data center, right? The second one could be latency. You have to keep your app as close to the large language model as possible. So, and you want maybe to have the use or the app as close to the user as possible. So if you are running an app for American-based users, you don't want necessarily to be able to talk to a large language model endpoint in Europe, right? Special use cases, sometimes the model themselves doesn't fit the use case that you need. And most cloud-hosted models like Gemini, you cannot actually fine-tune them. So you might need to take a foundational model, fine-tune it to your specific use case, and then use it. Privacy is another one. You don't trust cloud. That's just a very common thing, right? You might need to run in an air-gapped environment. You might need to run in your own data center. Cost is another one. Lots of times when you are actually talking to a cloud-hosted model, your cost is per token, and that could be too high or too low. So the way to think about it is the typical discussion around like total cost of ownership. Do you want to invest in your OpEx and just buy the hardware upfront, buy the software upfront, and run it, and then you can do whatever, or do you want to pay as you go, right? And then any of the combination of these multiple reasons, right? So with that in mind, Kubernetes basically, the Kubernetes as projects have existed for almost 11 years. And initially when Kubernetes was designed, it was really designed to run backend systems. APIs, backend applications, things like that. Then over time, we added running stateful sets applications, so you can run databases, you can do jobs, you can do a lot of things. But over the last 3 years, the projects, the open source projects, have actually seen an increase in the number of use cases related to running large language models. And the community have been responding very positively by introducing new features, and I'm going to cover some of those. Kubernetes gives you the most flexibility, right? It gives you sometimes the most performance, because you can literally just decide how many pods or how many models you're going to run per node. You can run on like evenly distributed models across all your nodes, or you can just design Kubernetes such a way that you like try to squeeze the most performance out of the node as much as you can. And then efficiency. specifically around the features like auto-scaling, where you can scale up and down very quickly. That's where Kubernetes actually comes with all these automations. And so I mentioned earlier that like large language models are not your typical web applications. They are kind of special web applications, or they're special workloads. So when we talk about large language models, there is actually multiple layers when you're running a large language model. You have the model itself, which you can optimize. Then you have the serving engine itself, wherever it runs on. So that's actually very important to keep in mind, because not all server engines support all the models. So you have to make sure that you have the right combination of model to the serving engine. And then you have the underlying infrastructure that you can also optimize, accelerators, nodes, et cetera, et cetera. So that's in terms of vertical optimization. In terms of horizontal optimization, we're talking about things like auto-scaling for the cluster itself, auto-scaling for the workload itself, and then anything related to caching. And so these multiple layers of optimizations are all important to look at to try to squeeze the performance out of your model, because each layer will give you few extra, tokens or extra latency or less latency that you can actually optimize for. So let's look at some of these layers. So these are some of the most commonly model running engines, serving engines you're going to see out there in the box. These are not all of them. There is some that are missing, but these are like the popular ones. You have something like VLLM is one of the most popular projects. It's a very actively contributed or actively maintained project, both by Google and Red Hat. You have Hugging Face, which has their own serving engine called TGI, text generation interface. NVIDIA has NIM, but they also have a different one. I forgot the Dynamo, I think. Then if you're looking at the framework called Ray, Ray has its own serving engine called Ray Serve. And then you have Jetstream and Olama, which you're probably familiar with. And so basically any of these models, any of these serving engines is going to be useful for you. You just need to look at which one actually A, supports your model, and B, supports the type of accelerators that you're going to run on. So a very common example would be that the NVIDIA NIM doesn't run on TPUs. It only supports GPUs. But VLLM, for example, does support both. There is a version of the VLLM that supports both GPU and TPU. Ray, the same thing. It also supports both TPU and GPU. So you have to start working kind of backwards from which model you're running, what kind of accelerators it run on, the most optimized, and then from there figure out which model you're going to be talking about, or which serving engine you're going to be using. And then when you are running large language models in production, you have to look at some indicators or some metrics. So the type of metrics we look at for LLMs are beyond just request per second, latency, P95 latency, et cetera, et cetera. There are things like time to first token, TTFT, so that's how much time it takes you to get the first token back from the model. The normalized time per output token, so that's how much time, or how much output token per second the model can actually produce. Time per output token, et cetera. I'm not going to read all of them. But these are all very important metrics to keep in mind that you have to actually monitor for to kind of assess the performance of your model. And they're kind of divided into this category, so latency and throughput, right? Luckily, with GKE, we have actually shipped a feature called out-of-the-box monitoring or out-of-the-box observability for AI serving. So if you are running any of these serving engines today, and this is not a full comprehensive list. We are adding more applications as we go. But if you're running it on top of GKE, you don't really have to do anything to instrument it. All of these serving engines comes with OpenTelemetry out of the box. Once you run it on GKE, we automatically detect that, and we build dashboards for you. So the dashboards are already there. So if you go today and spin up a GKE cluster and run Gemma using VLLM, just wait a couple of seconds, go to the observability tab or the workload tab, click on the Gemma, and then you click on the observability tab, and you will be able to see all the dashboards already. So it comes with latency, it comes with TTFT and all these metrics, and it also comes with error rates and a bunch of other models. And it also has built-in tracing. So we are actually deploying an agent that talks to a model. It will automatically generate spans, and then we can absorb those into the platform and show you the traces automatically inside the GKE platform. So this is something that is quite cool. You don't have to do anything. You don't actually have to pay for it. It's free. Now, some challenges for running large language models. I talked about the size. It's very important. But size has a direct impact on how long it will take for you to scale your model, right? So imagine you're running a situation where you have 5 pods running the model. Everything is handy-dandy. And then suddenly you get like a sudden increase in traffic, and you need to scale up. So if your cluster has to scale up by adding 1 node, which takes a couple of minutes, and then the pod has to spin up, then it has to download the model, which takes a couple of minutes, and then that model has to be loaded into the memory of the GPU, et cetera, et cetera. All of these kind of adds up, and you might end up in a situation where a scale-up event takes like 10 minutes, 15 minutes, etc. So yeah, typically this is how kind of like auto-scaling looks like. This is like the typical auto-scaling for any type of workloads on GKE, really. But specifically for models, the times can actually vary in terms of depending on the size of the model, depending on how fast you are scaling up, depending also on the availability of the resources in the region where you're scaling up, depending on the quota you have in your projects, et cetera, et cetera. So we tried to introduce a couple of optimizations. One of them is something called container image preloading with attached disks. So you can actually create a persistent disk that has the image preloaded on it, and then attach that persistent disk read-only to all the nodes in the cluster. So when the pod that is running the serving engine, like VLLM, starts, you just point it to the file system where the model is, and it will load the model automatically from the disk instead of downloading it from Hugging Face, for example, right? So this is pretty cool. And then if you don't want to use persistent disk, you can still use GCS with GCS Fuse, so Google Cloud Storage. So you can actually create a bucket, dump the model on the bucket, and then mount the model using the GCS Fuse driver to all your workloads. The key difference between these two features is that image preloading with attached disk will require you to restart the nodes if you need to update the content of the disk. With GCS Fuse, you don't need to do that. You just need to restart the pod itself. And then as long as the bucket is mounted on the node using GCS Fuse, the pod will be able to read it automatically. So we did some benchmarking, and we can actually like very quickly increase the time it takes to load a model by just attaching a disk. So it's a pretty cool feature. This is also combined with something called image streaming, you should probably have heard about. So GKE has this feature called image streaming, which speed up the time it takes to download the containers from artifacts registry. So the first time the container will be downloaded from artifacts registry can take a couple of minutes, but subsequent pulls will be much faster, because what we're doing is we're caching actually the image on a disk closer to the nodes in your cluster. So the first pull will be slow, but subsequent pulls will be much faster. Yeah, so this is how preloading image looks like. So on the right side, you have a Go tool that you run. You basically specify the projects, which image, and then which container do you want to load. And then on the right side, you just create the cluster, and then you add your -task secondary boot disk as a flag, and that will basically attach the container image as a secondary disk. Now, coming to this is, I think, the most interesting thing, optimizing accelerator capacity. So obviously, obtaining accelerator capacity is like the key thing for running large language models on GKE. And we have been doing a lot of work recently to improve what we call obtainability. So obtainability is essentially how fast and how easy it is for you to obtain the resources you need in whatever region you're running on. Starting with GKE Autopilot, which have existed for a very long time. I'm not going to rehash it here, what GKE Autopilot is. You all know it's a fully managed version of GKE. What we have done actually recently, which you probably might not know of, is we have removed the need for you to choose between GKE Autopilot and GKE Standards Mode by making Autopilot available inside Standards Mode. So today, it used to be in the past that when you create a cluster, at the creation flow, you have to choose Autopilot or Standards. But now you can actually create a Standards cluster and then enable Autopilot mode inside Standards cluster. So you might be asking, how does that work? Well, it works by basically giving you the compute classes that you are probably familiar with. So if you have used Autopilot before, you know that Autopilot has this concept of compute classes, which compute class defines what type of node you can get for the workload. So you tag the specific pod or the specific deployment with the compute class, and then we spin up the underlying node corresponding to the compute class you set. With Autopilot inside Standards Mode, we just add 2 more compute classes inside your cluster, inside your Standards Mode cluster. One is called Autopilot, and the other one is called Autopilot Spot. So you can take your existing pods that are running under Standards Mode and basically convert them into Autopilot by just adding the node selector. So this is actually also a great way for you if you have never tested Autopilot, you're not sure if it will work for you, you can keep your Standards cluster running, enable Autopilot mode, which doesn't do anything to your cluster, and then take one of your workloads, move it under Autopilot control, and then see if it works. And if it doesn't work, you can always revert back, right? And then you also know that we also made the compute class API available for you, so you can actually create custom compute classes. So now on standards mode, you can improve the way you obtain your resources in the cluster by creating a custom compute class in which you define the order in which you want the configuration of the nodes to be available. So you say, I want my nodes to be with L4 GPUs. If not, give me T4. If not, give me H100, spot, not spot, whatever. And then we will be able to actually respect that order in which the node configurations show up in the custom compute class. So here we're talking about basically moving from a static way of running workloads, which is you create the cluster, you create the node pools, and then you run the workload, and then you use taints and toleration to make sure that your workloads end up on the right nodes that you want, to a more dynamic way of doing things where you just create a custom compute class with multiple type of configurations in a specific order, and then GKE will respect, or we try to respect that. So if it doesn't get the first configuration, it falls back to the second, falls back to the third, et cetera, et cetera. So as I said, we have the standard compute classes which are available in GKE Autopilot today, but then you can create your own. Now, when it comes, so this is all good, and this all works actually for both GKE, for both AI and non-AI workloads. But when it comes into specifically large language models, you might need to get GPUs. And you probably are familiar with this, where you basically specify your GPU needs by specifying what we call a limit. So this is something leveraging what we call a device plugin, which is a Kubernetes feature that have existed for a very long time. For you running on GKE, you don't really have to configure anything. You just run GKE. GKE runs with or ships with the device plugin built in. And you basically say, give me 3 GPUs. And you can actually add another it's not visible here, but you can add another node selector which specify what type of accelerators you want, L4, T4, H100, et cetera, et cetera. This is actually pretty cool, but the problem with device plugin is that it's a very static way of defining resource needs, right? You just say, give me 2 number of GPUs. You still have to make sure that in your particular cluster, you have the node pools with the GPUs configured upfront, et cetera, right? Now, Kubernetes itself, upstream, have introduced something called dynamic resource allocation, DRA, which is an API that exists in open source Kubernetes. And this API have been introduced a couple of years ago with the concept of making requesting, allocating, and sharing hardware resources in Kubernetes kind of more dynamic, right? Hence why it says dynamic resource allocation. So the API itself is quite generic. It can work for all type of workloads, and I'm gonna touch on a couple of examples. What we have done is we have built a couple of drivers for integrating with DRA. So when you run GKE today, DRA is enabled by default, and then you have the drivers for GPUs and the drivers for networking and the drivers for TPUs. So the way it works is a little bit similar to, before I show you the next slide, it's a little bit similar to the concept of storage, if you are familiar with how storage works in Kubernetes, right? In Kubernetes, the way you define storage is that your platform admin will define the storage classes, which defines the type of storage available in the cluster. So your admin says, OK, here is a cluster. This cluster has regular disks, SSDs, and SSDs fast. So I'm just using random names here, right? And then you, as a developer or as a user, you would create a persistent volume claim, and then you point your persistent volume claim to a specific storage class. From your perspective as a user, you don't really care how that storage works. You just know that this particular class maps to this particular type of storage. DRA takes that concept and make it a little bit more generic. So in DRA land, you have a couple of types of resources. So you have something called a resource slice. The resource slice actually defines the type of resources that are available in the cluster. So those could be GPUs, could be network interfaces, could be anything in the future. Actually, I've been talking to some people working, like some software engineers at Google working on DRA, and they're even thinking about extending it to things like HSM, hardware security modules. Any type of hardware that you might need to actually attach to a pod will be available through the DRA interface. So the DRA becomes the standards API. As long as you have the driver for that particular hardware, that particular type of hardware installed in your cluster, it will just work. So this particular case, you describe what kind of devices are available in the cluster. So in this case, you say, OK, the device is an NVIDIA GPU. It has a product ID. It has 40 gigabytes of memory. And it has a certain number of cores. Then you, as a user, you create what we call a resource claim. So the resource claim is how you claim the resources you need. And the resource claim can be specific or generic. In this particular case, you say, I need an NVIDIA GPU with at least 30 gigabytes of memory and at least 3,000 F64 cores, FP64 cores. Then the scheduler, the Kubernetes scheduler, will basically match your pod So the resource claim is something that you will attach to the pod. And then once the pod is scheduled, the scheduler will basically do the matching. And in this particular case, you notice that in the resource claim, I did not actually specify the type of hardware I want. I did not say I want an A100 type of GPUs, unlike device plugin, because with device plugin, you have to be very precise what kind of accelerators you want, right? With DRA, you can just say, give me any sort of GPU accelerators that have at least 30 gigabytes of memory and at least this number of resources. And then the scheduler will automatically provision your cluster on the node that houses those resources matching the resource claim. So this is how it works for making the screen black. This is how it works for GPUs. We have actually announced last year. All right, somebody needs to log in. So last year we made. Oh, I need somebody to log into this computer here. Because my clicker doesn't work. All right, so I'm going to continue talking while they fix it. So last year, actually, we introduced the network driver for DRA. It's called DRA Net. And what DRA Net allows you to do is basically provision inter-chip high-speed network for doing multi-host inference. So if you have a large model that you need to run across multiple nodes, you need high-speed internet or high-speed connectivity between the nodes for something like RDMA, random direct memory access. So with the DRA Net, you can actually use Kubernetes to provision the underlying networks. And then this year at KubeCon EU, a couple of weeks ago in Amsterdam, we announced the release or the open source of DRA CPU drivers, and then NVIDIA announced the open source of the GPU drivers. So actually, DRA plus the drivers are something that you can even use outside of GKE, because it's just a generic interface which is available in Kubernetes upstream, and then as part of the, so that's DRA. So that's DRA. And then the next thing I'm going to talk about is a feature that I'm not quite sure how many of you, so I'm going to ask, how many of you have heard of GIQ, GKE Inference Quick Start Guide? As I suspected, no one. OK, good. All right, so if you've never heard of this, this is actually a really cool feature that is available both in the interface and in the CLI in G-Cloud. What it is, essentially, it's an opinionated way of running large language models. So using the web UI or the command line, the G-Cloud command line, you can basically tell us which model you want to run. We don't support all models. We support, I think, 10 or 12 of them. The famous one, Qwen, DeepSeek, Gemma, et cetera, Llama. So you can list which models are supported, and then you can say, OK, create me a configuration that can run this particular model at this particular target TTFT. So you can even specify the target time to first token. And then we will generate the configuration. So you can think about it as working the other way around. Instead of you configuring the cluster and trying to figure out which resources you need in the cluster to be able to run a model, you go, I want to run this model. Tell me how I should configure my cluster. And so it has multiple models that are supported, multiple open models that are supported. You can list them. In the interface, you can see here that we are basically saying, I want to run Gemma 7B using VLLM as a serving engine. And I want my latency to be like 5 seconds. And then you will see in the bottom, the recommendation part, that part will be changed as you are sliding that like latency bar, or as you are changing the model you want to run, right? So this is a really cool way to actually generate configuration out of you trying to run an existing model. So if you have never done large language model inference on GKE, this is a really good way to get started, hence why it's called Quick Start Guide, right? So look into it, GIQ, it's pretty cool. And then now we're going down a little bit even down the layer. So we talked about optimizing the models with precision and things like that. We talked about optimizing the serving engine with like preloading container images, image streaming, et cetera, et cetera. Then we talked about the accelerator layer. So now I'm going to go down a layer of talking about optimizing the network itself. So a typical large language model serving will look like this. What you would want to do in production is you don't want necessarily to just like run large language model and then run the kubectl port forward to be able to talk to the model. You want to put a proper load balancer in front of your model so that users can basically talk to a single endpoint to multiple models. Now I'm going to stop a second here and explain something super quickly. Most open source serving engines like VLLM, Llama, etc., they support something called the OpenAI spec. So OpenAI, a couple of years ago, they came up with a standard interface, a standard API, and this API is actually supported by most open source serving engines. So the interface itself, the API is standard. So if you are going to, for example, run VLLM, VLLM has a container image called VLLM-OpenAI, which is the VLLM container plus the OpenAI interface, right? And one of the things you will notice probably if you have done this before is when you try to call a large language model using the OpenAI interface, you have to specify the model ID in the request. It's not in the path. So usually you will request your HTTP/whatever host/v1/chat, and then you will specify a payload which have a very specific structure, and one of these fields in the payload is the model ID, right? So we all know that our load balancers, Google load balancers, whether you configure them through Ingress or through the Gateway API, they don't have a way to do intelligent routing based on the core of the request. They can only do routing based on the path, right? So how do we solve this? So the way we solve this is through something called the Gateway API inference extension. So you know what the Gateway API is. It's the next generation Ingress, which have existed for a while now. A couple of years ago, the community have created something called the inference extension, which is an extension of the Gateway API to be able to do inference. And the way this works is that it introduces two new objects. One is called inference pool, and one is called inference objective. So unlike the standard Gateway API, which has gateway class, gateway routes, TLS, ADP, HTTP, et cetera, now we're introducing these two objects called inference pool and inference objective. So the inference pool defines the pool of all the inference engines. So those are the pods that are running the large language model. The inference objective allows you to define like latency requirements. And then the Gateway API, so the inference extension of the Gateway API introduces something called the endpoint picker, EPP, the endpoint picker extension. So what the endpoint picker does is essentially acts as a router where the request comes to the user through the V1 chat completion interface. So that's the OpenAI interface. It goes to the gateway. The gateway will forward that request to the endpoint picker. And then the endpoint picker will read the core of the request. It will read the payload and then return to the load balancer which pods that request should be going to. So this is the first implementation of the inference extension. But the goal with this over time is to make that endpoint picker even more clever. So making it, for example, aware of the load on the pool, so it knows which pool are busy and which pool are not busy, so it can actually route to the non-busy backends, right? And why this is important? It's important because network traffic for large language models is not similar to how web network traffic looks like. When you're running web applications, your network profile, network traffic profile, is very small, very fast requests. With large language models, you have very uneven requests coming into your large language model. Some of them could be small. It could be a user saying hi to a bot. Some of them could be large because it could be a user basically writing a very large prompt to a model to generate a picture, to do some refactoring of code bases, et cetera, et cetera. So the size of the requests vary. And so typical traditional load balancers doesn't work in this case because most load balancers does round robin. So they basically forward the calls based on the request count. So first request goes to backend 1, second request backend 2, et cetera, et cetera. So the problem with round robin type load balancers is that you might end up actually wasting GPU resources because you might end up having pods that are super busy, and then more requests will just pile up, waiting for the existing request to be finished, and then pods that are just processing super small requests and then doing nothing, right? Also, most load balancers have no way to actually read accelerator-specific traffic or accelerator-specific metrics. So you can, for example, configure load balancing based on CPU and memory utilization, but it's very hard or almost impossible to configure it based on KV cache states, GPU accelerators, GPU availability, et cetera, et cetera. And also the size of the request, as I talked, sometimes actually the request itself could be bigger because it could be that the user opened the session and the session will stick for a couple of minutes because the user sent a request, the model is processing the request, and think about it even, it's even kind of more complicated when the user or if the user enables token streaming. So if you enable token streaming where you send a request and then you stream the tokens back to the user as they're getting generated, then your connection will be too long. So traditional load balancers doesn't work in this case. So The inference extension is one way of solving this problem through the endpoint picker, where we can actually intelligently route requests to the backend depending on what type of request it is. But you might sometimes even want to do even more. You might, for example, want to prioritize traffic, where you can say, OK, I have a pool of large language models, and they're all powering my website. Now, most of the time, I have people sitting on my website talking to a chatbot, asking it random questions. Give me a recommendation for a product. Give me a picture of a product. Tell me which product goes with which, et cetera, et cetera. But sometimes, imagine you're an airline, and there is a strike, and then all your flights get canceled, and suddenly you have a flood of users coming to your chatbot trying to get resolution. So you might want to actually deprioritize some type of traffic and prioritize some other type of traffic based on your business needs. That's where this new project that was introduced a couple of years ago, and last KubeCon in Europe, we donated LLMD to actually the CNCF, the Cloud Native Compute Foundation. So LLMD is a project that is introduced to define what we call well-lit paths, or well-architected paths, or well-tested paths for large language model inference on Kubernetes. And so as of now, it actually has 3 well-lit paths. It has something called intelligence inference scheduling, which is an architecture by which you actually split the decode phase and the prefill phase of the inference pipeline into specialized nodes. So I don't have time to go into the details, but basically when you're trying to do inference, there is the pre-phase, which is prefill, where you kind of process the request, load it into memory, and decode is when you generate the requests. And these 2 types of requests have different resource requirements. One of them is memory bound, the other one is a CPU bound. So with intelligent inference scheduling, we can actually split those requests into individual nodes that have the dedicated hardware that can do this type of request super well. So this is how the architecture of LLMD looks like. Again, LLMD is open source. It's available on llmd.io. And then there is a Helm chart that allows you to actually deploy LLMD into GKE. So behind the scene, it just uses VLLM. It has an implementation of VLLM. And then it has some implementations of some specific NVIDIA technologies like NIXL and DCN for memory sharing across nodes. And then it uses the inference gateway. You can use Envoy, or you can use the GKE inference gateway, which is also Envoy-based, but it's managed. And then it has an inference scheduler, which is a component that does all this like intelligent scheduling based on utilization. And then it also has the body-based routing, which I talked about earlier, which can read the model ID from the body and then forward the requests to the proper backend. So it's something that I really highly recommend that you look at. And I have 7 minutes. I'm almost done, so I want to leave some time for questions. So to recap, we talked a little bit about optimization on multiple layers. Optimizing Kubernetes or GKE to run large language model happens at multiple layers, starting from the model itself, then going down to the serving engine, the choice of the serving engine, the way you're going to load the model, the way you're going to make the model available, et cetera, all the way down to optimizing the infrastructure across accelerators, across networking, and across the load balancer side. And that's it. I hope this was useful. I would appreciate if you give me some feedback on the application. If you go to the app, you can find my talk and then provide me feedback. And thank you so much. The clock in front tells me I have 7 minutes, so I think I have there are some people with microphones that can run around and give you a microphone. Yeah, there is one question in the front. Oh. Yeah, you shout your question, I'll repeat it. Yeah.
Let's grab the other one.
Yeah, the question is, do we plan to support GRIQ? We don't really have a driver for GRIQ today, and we don't have them on Google Cloud yet. I don't know what the roadmap looks like. I can probably ask later, and maybe if you find me during the conference, I might have the answer by tomorrow. I can ask some PMs, but we don't have it yet. But I'm quite sure that by the moment GRIQ becomes available in the platform, if there is interest, we'll probably build a driver for it. Yeah. But for now, we only have the driver for networking, TPUs, and then GPU one is open source by NVIDIA. But it's available on GKE, of course. Of course. Another question?
Over here.
Yes.
Hi, so I had a quick question regarding auto-scale pods in Kubernetes itself. So let's say I have already have a huge GKE cluster, and I want to add a pod which has minimal GPU requirements. Does it involve spawning a completely new node with all the like CPU, memory, and stuff like that, or does it just give me like, am I a shared tenant on a separate node? Here in this case, I'm trying to reduce my cost. So if I have two such pods, I don't want to create multiple nodes for different use cases, right?
Yeah, so that's a good question. There are multiple ways to answer your question. So the simple way is basically if you have an existing cluster with a certain number of nodes, with a certain number of GPUs, and you have pods already using these GPUs, and you're trying to spin up a new pod, sorry. If that new pod requests a certain number of GPUs that are not available on the cluster, then the cluster autoscaler will kick in and then create a new node, right? That's like the simplest way. And this is particularly true if you are using the device plugin with static GPUs. So let's say, for example, you have two pods. You have a node with 8 GPUs, and you have two pods that each request 4. So they will be all together put on the same node, right? But then if a new pod comes up and requests another 4, then there is no more GPUs available, so GKE will spin up a new node for you, right? But to answer, like the more complex way of answering your question is that's what DRA is supposed to solve. With dynamic resource allocation, you might not run into this issue because you can actually even like slice or share GPUs across multiple workloads, right? So that really depends on how the workloads are running right now, what sorts of resources they're claiming, and what like device plugin. Kubernetes treats it as a simple scheduling problem where you have resources available, clusters like workloads using them, and the new pod requesting resources. It will be put in the queue, and then the cluster autoscaler will spin up and create a new node for you.
But do I have to care about whether the accelerator has MIG or time slicing or whatever it's available, and then swapping in and out of jobs and stuff like that on the?
With device plugin, you can actually use GPU sharing with device plugin, but with dynamic resource allocation, you don't have to care. It just works out of the box.
Okay, thanks.
All right. There is a question here in the front.
So I believe Jensen Huang said that latency and throughput are fundamentally like opposed.
Yeah, they're mutually exclusive.
Do you believe that as well? And do you see LLMD as a solution for that? Because I believe CUDA abstracts that through software.
Yes, I think LLMD is one of these projects that is supposed to try to give you like the right balance between latency and output. But the right balance between latency and output is also a factor of the type of models you're using. Some models are actually more suited for some tasks compared to other models. So with LLMD, you can actually go like a step further, where you can basically define policies that will look at the requests and then forward the request to the right model based on what type of request it is. Does it have media? Does it not have media? Is it like a big request? Is it a small request, et cetera, et cetera? So as it stands right now, it doesn't have all these like very fine-grained policies that can define all these routing decisions, but that's the goal long term, is to build all of these things. So you might have a single load balancer with a single interface, and then you go through LLMD, and LLMD goes like, okay, this is a gen media, like a picture generation request, so I'm going to send it to this particular model because I know that that model knows how to do that pretty well.
Cool, thank you.
Thank you. Any other questions? I have a minute and a half almost left. All right.
Yeah. Thank you so much for the presentation. My first question, maybe it's not really directly related to the subject, but you didn't mention the Cloud Run as an option to run LLM models. Is there a reason for that?
That's a very good question. I mean, the talk is GKE, so I didn't mention Cloud Run.
I see.
But, I mean, you can run large language models in Cloud Run. Cloud Run have a couple of limitations. It only supports 3 types of accelerators today. So the L4, the H100, and the RTX 6000. And it doesn't support multi accelerators per pod. So when you run a Cloud Run service, you can only attach 1 accelerator to the service. Unlike GKE, where you can attach multiple GPUs.
Yeah, for sure. Thanks. When we have GPUs available in the region, I mean, one of the suffering issues that we have is like GPUs are not available in the region.
In all the regions?
All the regions.
Yes.
So we have to choose, how to say, which model we can run on which kind of compute support. And the second question is from a pricing perspective, comparing the standard GKE and autopilot, which one do you recommend to use in order to run LLM models?
I would recommend to go with autopilot and custom compute classes. From a pure cost perspective, there shouldn't be any difference, but that depends also on the type of workloads. Like the pricing for GKE autopilot and standard is similar, right? The GPU core or CPU core or memory or network traffic is the same pricing. It's just like the pricing, of course, depends on the region, but like it should be fairly similar. But the thing with the autopilot is that you can actually, you avoid over-provisioning because autopilot will scale up and down depending on what you're trying to run. So if you have some sort of like horizontal pod autoscaler configured on the model where it will scale up when there is demand and scale down when there is no demand, then in this case, autopilot sometimes might be like cost effective compared to standards, because in standards it's very static, right? The way you define resources is very static.
Yeah.
And with autopilot in standards mode, you don't have to choose anymore. You can actually have both in the same cluster and then test on benchmark and figure out which one works best for you.
Yeah, I see. Thank you so much.
Make sense? All right. That's it. Thank you so much. I hope this was useful.